Okay, and welcome back. So hopefully you've already seen integration video 1, and so this is integration video 2, where we're looking now at higher order Simpsons methods. And the basic idea is that before, with the trapezoidal rule, we were approximating the function as a line. And so we're going to find here that higher order polynomials like a quadratic or a cubic can be alternative strategies that have even lower error because they'll better follow the curvature of your function. This is as opposed to is a different strategy than when we are breaking up into smaller and smaller step sizes, which is what we did with the multiple application trapezoidal rule. So the basic idea with Simpson's 1/3 rule is that we're approximating our function as a quadratic. And so if I write out here, actually, I'll call this x0. If you have 3 points along your function, and you have a f of x1, f of x2, and f of x0, then what we're doing here is we're assuming that the function is shaped like a quadratic. I'm going to do my best to draw a quadratic through that function. So the key here is to notice that this does not go, this goes exactly through these 3 data points, but it does not exactly follow our original function. Okay? So we're going to say, like, whatever is happening with this function in between those 3 points, we're not going to use that information. We're going to assume that this is a quadratic. Okay, and so the key point here is that rather than using 2 points, it's important that this requires 3 points. 3 points along that line. And so this is on the interval from A to B. We're just saying that this is one quadratic for now. And so what we're doing here is approximating f as a quadratic of order 2. And so the overall equation is going to look similar to what we had before. We have our width, b minus a. But we have now a different approximating series for the average height. We have f of x0 plus 4 f of x1 plus f of x2 over 6. So this term is the height. Okay? And so the error for these, for a Simpson's 1/3 rule is has a 2880 in the denominator, which is much of a going to be a much smaller error than what we had seen with the similar equation for the trapezoidal rule. So let's take a look at an example where we apply this new equation. So I'm going to first create, so we're still trying to integrate the same function, 8 plus 4 cosine x, from 0 to pi over 2. So I'm going to redraw my little number line here, just to make it clear that we want 3 points, 0, pi over 2, and so this is going to be pi over 4. Okay? And then we've got our true answer at the bottom. We're not going to look at that for now, just going to take a look at that at the end. And so we're going to integrate from 0 to pi 2 fx dx, which is approximated by our Simpson's 1/3 integration formula. So it's b minus a, which is pi over 2, minus 0, and then we have a f of x0, we have a 4 times f of pi over 4. And then we have the x2, which is pi over 2, plus f of pi over 2, all divided by 6, okay? And if you plug that into your calculator, you should get 16.575, and the relative error on that is pretty darn small. It's negative 0.055%. Okay, so that's how we use Simpson's one-third rule integration. Just like the trapezoidal rule, you can also do multiple application Simpson's one-third rule. And so the basic idea here is that it starts out, so that, again, this is the average width, and you've got a more complicated set of formulas for the average height. Notice here that we have two series. This is going over odd values, and this one is going over even values. And so this is a combination of terms that will be equivalent to adding up each of these quadratic functions that are going together. And so this is for n segments, which means it's going to require information about these functions at n plus 1 points. Okay, and notice how the error is an awful lot smaller than before. So this is, remember with the trapezoidal rule, it was on the order of 1 over n squared, and here our error is on the order of n to the 4th. So this is going to be a much more accurate method than what we had seen before. Okay, and then finally there's Simpson's 3/8 rule. So if it said, okay, if a line isn't good enough, if a quadratic isn't good enough, then you can approximate your function as a cubic. And so that gets even closer to the shape of your original function. And with this formula, you expect that the error is even smaller than it would be otherwise. One key point here is that this requires 4 data points, whereas the Simpson's 1/3 rule required 3 data points. And so really one way to decide on these is whether you have an odd or an even number of data points that you need to integrate over. And notice here is that the error is smaller than even the Simpson's 1/3 rule. All right, so this is Simpson's 3/8 rule. So so far we've discussed really 3 different ways of integrating. One is the trapezoidal rule, or there's the Simpson's 1/3 rule, which approximates as a quadratic, or there's the Simpson's 3/8 rule, which approximates as a cubic. And so as you go higher order terms, it requires more data points. We had 2 here, then 3, then 4, but we find that if you have those data points, they can lead to smaller errors in your numerical computations. Finally, it's helpful to notice, if you want to remember these, that all of the weighting coefficients, these are just the original data points that are weighted by different amounts, and so you'll notice that they all weight, the weighting coefficients add up to 1. So that can be helpful in remembering these terms. So to summarize what we talked about, that the trapezoidal rule approximates our function as linear, Simpson's 1/3 rule as a quadratic, Simpson's 3/8 as a cubic, and there are really 2 different ways of approximating an integral if you want to get better and better results. So one is to use a higher order function, and remember that's just the same way as in Taylor series. If we took a higher order Taylor series, we got more accurate results. And so here, taking a higher order polynomial, you get more accurate results. Or you can break it up into a whole bunch of different pieces using the multiple application rules, and that is another way of getting smaller errors. So I hope that's helpful to you. On your problem set, what you'll be doing is applying these integration rules in order to integrate actual biomedical data on a hand position using an accelerometer data that I had in the lab. So hopefully that's useful to you, and I'll see you next time.